Questions 11 through 20 on the 2016 Grade 12 AMC 12B. How many squares whose sides are parallel to the axes and whose vertices have coordinates that are integers lie entirely within the region bounded by the line y is equal to pi times x, the line y is equal to negative 0.1, and the line x is equal to 5.1. So here's a very nice diagram, in my opinion. This line right here is your y is equal to pi x. And this line right here, this one going top to bottom, is x equal to 5.1. And probably a little difficult to see. If you notice, there's two lines here. One, of course, represents the x-axis, and the one below it is what's represented by y is equal to negative 0.1. Okay, this is an interesting question. What you have to do is concentrate on the side length of the square, right? They're squares. So we're going to talk about side lengths of 1, 2, 3, 4, and 5. And I don't think we need to talk about anything greater than 5. Okay, let's start. So let's start with 5. If my square has a side length of 5, first of all, can I fit it in? Well, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. I don't think I can fit a square that's 5 by 5, as you can clearly see, because it has to be bounded by that line, this line, and that line. So that's the key. Okay, so that means my 5 by 5 square has 0 ways of doing it. Okay, no problem. Move forward. 4 by 4. Well, I think I can do a 4 by 4. Or can I? Well, I've got 4 here, but what if I go up 1, 2, 3, 4? Oops. I go beyond the boundaries, which is a little unexpected that this is also 0, but no big deal. Okay. Now what happens is things start to get a little bit more, not necessarily complicated, but a little bit more time consuming. And what is important, in my opinion, is to figure out what these points are. I think it's important because it will help us. And that's pretty straightforward to figure out because the x-coordinates are 1, 2, 3, 4, and 5. And those points on the y-axis can be easily figured out by y is equal to pi x. And you can use pi is equal to 3.14. So this would be 3.14 because it's 1 x. This one here, when x is 2, it would be approximately 6.28. Right? So no tricks here. I'm just putting in the values. This would be approximately 9.4. And then this guy up here would be 4 times pi, which is about 12.5. So diagram is not perfectly drawn to scale, but it gives you a pretty decent understanding. Okay, so now let's talk about the 3 by 3s. 3 by 3, if I use this as my base, can I fit it in? Yeah, because there you go. That's where knowing that point is important because it has to be greater than 3. That's the only way I can fit it in. All right, so I got 1 so far. After all that, I've only got 1. And the answer choices are quite a bit bigger than 1. But what about if I stay here, can I move up? And the answer is no, you go beyond the boundary. Okay, no problem. What if I move over this side? Well, I got 1 here. If I go up, 2. If I go up again, 3. And if I go up again, 4. And that will work. So I've got 4 if I moved over a little bit. So 1 plus 4, and that gives me 5. All right, so making some progress here. Now let's talk about 2 by 2s, the next one here. 2 by 2s, so if I have that as the base, that will work, that will work. So that's 2 I got. Okay, if I move the base over here, I'll be able to get 1, 2, 3, 4, and 5. 5 of those when I move the base over. And then if I move the base over to here, 1, 2, 3, 4, 5, 6, 7, 8. And I think that's it, because the next one, it would be outside of the boundary. All right, so I got 8 here. So that is 15. And then now finally the 1 by 1. Okay, so this one obviously will have the most cases. 1 by 1, 1, 2, and 3. All right, so that's 3. 1, 2, 3, 4, 5, 6. If the base is here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And finally, if the base is on here, from there to there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there we go. That completes it. So this would be, let's see here, what's that? 12 plus 12, 24, 30. So the total is 30 plus 15 plus 50. That's 30 plus 15 plus 5, which is 50. I got a little ahead of myself there. So number 14, the answer is D. It's a pretty cool question. All the numbers 1 through 9 are written in a 3 by 3 array of squares, one number in each square, in such a way that if two numbers are consecutive, then they occupy squares that share an edge. The numbers in the four corners add up to 18. What number is in the center? Well, first just talk about what they mean by share an edge. I'm sure some of you understand. Some of you may not. Share an edge means like that. So numbers are consecutive, for example, 5 and 6. They would have an edge between them. That's what all that means. Share an edge. Okay, let's figure out what to do here. This is a little bit of trial and error, which is always a bit of a time drain, but you know, it is what it is. Okay, so let's make my 3 by 3, and here we go. Well, my first square, I'll just keep it simple. I'll just try to go in order. 1, 2, 3, 4, 5, 6, 7, 8, 9. Everything shares an edge, right? Does this work? Well, according to my share an edge part of the question, it all works because all consecutive numbers share an edge. But I've also got to satisfy this criteria, which the numbers in the corners add up to 18. Let's see, I got 3, 5, 8, 1, 7, 8, 16 is the corners. Corners here, the sum is 16, so that's no good. Okay, no problem. That was a pretty decent first attempt. Let's try again. So I got to somehow get this to have the corners add up to 18. All right, let's try again. 1, 2, 3, 4, 5, 6. At this point, if I put a 7 here, I'm pretty much done the same thing, right, as this one. So I've got to get the corners add to 18. This one added to 16, so I get 2 more. So 2 more would not be 9. So put a 9 here. And then 8, and then 7. So let's see, do I meet both criteria? Do they all share an edge? I believe so. 6 and 7 shares an edge there. 7 and 8 share an edge. 8 and 9 share an edge. Okay, so that's all fine. And do the corners add up to 18? 8 and 10, they do. So 18 is the sum of the corners. And that's it. With a little bit of trial and error, I figured it out. And the number in the center is a 7. So number 15, the answer is C. Alice and Bob live 10 miles apart. One day Alice looks due north from her house and sees an airplane. At the same time, Bob looks due west from his house and sees the same airplane. The angle of elevation of the airplane is 30 degrees from Alice's position and 60 degrees from Bob's position. Which of the following is closest to the airplane's altitude in miles? Let's first draw a diagram to illustrate this question, and then we can explore how to tackle it. So the airplane is going to be up and down like that, and then I will draw lines to connect it to where Bob and Alice are. So Alice is here represented by A, Bob is here represented by B, the plane is here represented by P. And then these are right angles because those are basically either north or west or some direction like that. So those are going to be right angles. And then the distance between Alice and Bob is 10. And then the angles, they tell me the angle of elevation from Alice to the airplane is 30. So this is 30. And then for Bob, it's 60. So very quickly we can get the other angles. This is going to be 30, and this angle in here will be 60. All right, I think we have everything we need to calculate the altitude. The altitude is from there to there, and I'll just call that h for height, and here we go. So using 30, 60, 90 triangles, if this is x and this is y, the distance from here to here y and the distance from here to here x, h over x using 30, 60, 90 triangles is going to be root 3 over 1. So therefore, x is equal to h over root 3. And again, using 30, 60, 90 triangles, we can get a relationship between h and y. H over y is equal to 1 over root 3. So that means y is equal to root 3 times h. And now we plug it into this Pythagorean relationship, and that will help us solve for h. So x squared plus y squared is equal to 10 squared. X is h over root 3 squared plus y, which is root 3h all squared. 10 squared is 100. So this is h squared over 3, and this is 3h squared is 100. Multiply through by 3, and you get h squared plus 9h squared is equal to 300. 10h squared is equal to 300, and therefore h squared is equal to 30. H therefore is root 30. And of the answer choices, the one that's closest to root 30 is about 5.5. So number 13, the answer is E. The sum of an infinite geometric series is a positive number s, and the second term in the series is 1. What is the smallest possible value of s? Some of you may know that the sum of an infinite geometric series is given by a very nice formula, a over 1 minus r, where a is the first term and r is the common ratio. Now you might not be convinced that this is possible, because if it's infinite, wouldn't it just keep on going? And the answer is, well, this only works when r is less than 1. So I guess that's the key to understanding or being convinced that the formula will work. All right, so let's keep going here. And for the sake of completeness, r can also be greater than negative 1. All right. Okay, let's begin. The second term, they tell us the terms are going to be a, ar squared, ar cubed, and so on, right? But they don't give us any of the terms except the second one. They tell me that this guy is equal to 1. So, okay, ar, therefore, is equal to 1. So I can isolate a equals 1 over r and put that into here. It's always better to have less variables rather than more variables. So this becomes 1 over r, and that stays 1 minus r. Invert and multiply, I get 1 over r times 1 over 1 minus r. So this is 1 over r minus r squared. Okay, so my goal is to make this guy as small as possible. Well, how do you make that as small as possible? And the answer is I don't know. But I do know one thing, that if I make this denominator as large as possible, then s will be as small as possible. So to minimize s, I must maximize the denominator, which in this case is r minus r squared. I think that will be sufficient. Okay, so let's now concentrate on trying to maximize r minus r squared. Okay, so we have r minus r squared, and we're trying to maximize this guy. I'm going to flip it here, write it like that. And then some of you know how to do this. You do it by completing the square. Let's factor out the -1, and then we get minus r. Then what you do is you take half of this coefficient, which in this case is -1. Well, the coefficient is -1. You take half of it, which would be -1/2, and you square it. When you square -1/2, you get 1/4, and then immediately you have to subtract that. And then the good news is that those guys factor beautifully. R minus 1/2 all squared. And then kick this out, but don't forget to multiply by that -1. So that'd be plus 1/4. So this basically is like a parabola that opens downward. And when r is 1/2, it's going to be 1/4. So something like this, right? Like that. So what that essentially means is that when r is equal to 1/2, we have the maximum value of that function, and that is 1/4. So the max value of this guy after completing the square is 1/4, and that happens when r is 1/2. Okay, so I got the max value of this guy, so that's what I needed to do to substitute back into there. And when I do, I get s is equal to 1 over the max value, which is 1 over 4. The max value of that is 1 over 4. And therefore invert and multiply, and you get s is equal to 4. And s is equal to 4 will be the minimum value of s, smallest possible value of s. So number 16, the answer is E. All the numbers 2, 3, 4, 5, 6, 7 are assigned to the 6 faces of a cube, one number to each face. For each of the 8 vertices of the cube, a product of the 3 numbers is computed, where the 3 numbers are the numbers assigned to the 3 faces that include that vertex. What is the greatest possible value of the sum of these 8 products? Let's draw a cube, and let's try to illustrate this question. Well, the numbers, I'm going to call them letters because I don't know where they go. Those are the numbers, of course, but I don't know where the 2 goes and where the 3 goes and so on. So what I'll do is I'll put F here. The numbers I'll represent A through F, A, B, C, D, E, F. The F I'll go at the front. I purposely put F there because F for front, because I don't want you to get confused. And the B I will put at the back, purposely B for back. And then the other letters, doesn't really matter. I put A on this side. C I'll put on this side. D at the top. And then E at the bottom. And what's left? I think that's it. 1, 2, 3, 4, 5, 6. Okay, I've assigned them all. Now, at each corner, I will put the 3 that basically meet. So for each of the 8 vertices, the 3 numbers are the numbers assigned to 3 faces that include that vertice. So for example, this guy will be BCD, right? Because it includes the back, it includes the top, and includes the side, that vertice. All right, so similarly, this is BCE, this is CEF. This vertice, the product would be AEF. This guy, ADF, ABD, and this one in here, what is it going to be? ABE, I believe. Yeah, ABE. And finally, the top one, this one, CDF. Okay, hopefully that isn't too messy. All right, now we got to calculate the sum. The sum is all of those together. So we got ABD plus ADF plus AEF plus ABE plus a BCD plus BCE plus CDF, and one last one, CEF. Okay, so how does this help us? Well, we have to do some factoring. If I factor out an AD, I'll get B plus F from this guy and this guy. All right, next one is if I factor out an AE, I get F plus B plus from this guy and this guy. And then factor out a BC, and I'll get D plus E from this and this. And then finally, CF will give me D plus E. And of course, I've factored those two from there. All right, I think making some progress. I sincerely hope so. B plus F can be further factored because it's common to this and this. And that gives me AD plus AE. And then D plus E is common to the other two. And that gives me BC plus CF. Okay, I think I can further factor this B plus F times an A plus a D plus E. And then plus D plus E, I can factor out a C, I believe, and that will be B plus F. And then I think the B plus F and D plus E is common to both. Okay, so having some very good success here with factoring. And then that factors to A plus C. All right, great. It's a pretty decent end result. So now what we have to do is look at the fact that we are to choose from 2, 3, 4, 5, 6, 7. Those are the numbers, and we got to maximize that. Okay, so at this point, it's just some trial and error. If I put 2, 7, 3, 6, 4, 5, like that, it'll be 9 plus 9 times 9 times 9, and that's 729. And if you fiddle around with this, you will find that that is actually the largest result. So there you go. Greatest possible value, the sum of those 8 products, 729. So number 17, the answer is D. In how many ways can 3, 4, 5 be written as the sum of an increasing sequence of 2 or more consecutive positive integers? So 2 or more. So we can have 2, 345, and this would be 2x plus 1 is 345, and solving we get x equal to 172. So that means my numbers are 172 and 173. And in a very similar way, we just keep doing this. 2x plus 1 plus the next guy, which would be x plus 2. That equals 345. And that would be 3x plus 3 is equal to 345. Solving, we get x is equal to 114. So that means x will be 114, 115 for x plus 1, and 116 for the next guy. And you just continue like this. And this is the long way because I want you to understand it. You just keep going like this, and then you do the next one, which would be 3x plus 3 plus x plus 3 this time is 345. And that would be 4x plus 6 is equal to 345. But this time, x will be like 84.75, which is not an integer. And they have to be integers. So this is an invalid solution. It doesn't work. So you just keep continuing like this. And for the sake of time, I'll just give you the ones that are successful. When you do all the way from x to ... x plus 4, that one works out. X is equal to 67 here when it equals 345. And I'll let you do the algebra. So this, I'll put that there. And then it also works when you go up to x plus 5, all the way up to x plus 5. That one gives you a value of x is equal to 55. It also works when you go all the way up to x plus 9. That gives me a value of x equals 30. And there's a few way out there. You have to go all the way, unfortunately, to x plus 14. That one works. That actually gives me x is equal to 16. And one last one that works is all the way out there to x plus 22 is equal to 345. And that gives me x is equal to 4. So the ones that work out are this guy, 67, 55, 30, and 4. Oh, and this one also. So how many is that? That's 7, right? So the answer is 7. And if you have a shortcut, which I sincerely hope that you do, please use it. And I'll give you a little bit of a hint. The shortcut involves prime factors of 345 and the median. So this is the way I would do it in practice. But then on a math contest, of course, you need to find a shorter way of doing it because this is very time consuming. In triangle ABC shown in the figure, AB is 7, BC is 8, CA is 9. AH is an altitude. Points D and E lie on sides AC and AB respectively so that BD and CE are angle bisectors intersecting AH at Q and P respectively. What is PQ? Well, just a very quick primer about angle bisector theorem. If you have any triangle like this and then you bisect an angle, we have a relationship between the sides. So if this angle has been bisected to make it theta and theta, and this side is A, this side is B, this side is C, and this side is D, the relationship is that A over C equals B over D. All right, so here we go with this very interesting question. All right, step 1 is going to calculate the area, and I'm going to use Heron's formula. And Heron's formula, first we calculate the semi-perimeter, which is going to be 7 plus 8 plus 9 divided by 2, and that is 12. And then the area is S times S minus A times S minus B times S minus C, all under the square root sign. So S is 12, 12 minus A, well, A is, you can use 7, for B I will use 8, and for C I will use 9. So this basically becomes A is equal to 12 times 5 times 4 times 3. And that is simplified 12 root 5. So we got the area of that big triangle. Now step number 2. We have to try to get the value of AH. Well, the area is 12 root 5, but the area can also be calculated in another way, which is that as the base and that as the height, since that AH represents an altitude. So 1/2 base, which is 8, times the height, which is AH. And therefore AH will become 12 divided by 4, which is 3 root 5. And there we go. So making some excellent progress here. Number 3. That is an altitude, right? So that means this is a right angle. So you can use Pythagoras to figure out this distance right here, HB. So AH squared plus HB squared is equal to AB squared, which is 7 squared. AH squared is 3 root 5 squared, so that's going to be 9 times 5, which is 45. And then we have HB squared, and that's 49. So therefore HB squared is 4, and therefore HB is 2. So there we go. This is 2, and therefore from here to here will be 8 minus 2, which is 6. So I'll just put a 6 right there. All right, moving right along. Now we use the angle bisector theorem, and we're going to use it on 2 triangles. The first one is triangle ABH, and then we'll use it on triangle ACH. Because remember, those angle bisectors were BD, so this is theta and this is theta, and CE, so this is alpha and this is alpha. All right, so here we go. On ABH, it would give us HB over QH is equal to 7 over AQ. But HB, I know, is 2. So I don't need to put HB, I can just put 2. So that helps me out. And then I can just get a ratio now. 2 over 7 is equal to QH over AQ, like that. And also we know that QH plus AQ is equal to AH, right? QH plus AQ is equal to that entire distance AH, and AH we just figured out was 3 root 5. So since these are in the ratio 2 to 7, we put them in the ratio 2 to 7. So I can put like 2a plus 7a is equal to 3 root 5, like that. And therefore 9a is equal to 3 root 5, and therefore a is equal to root 5 over 3. That's very helpful because now we can calculate one of these. Either one. Let's calculate QH. Well, QH is designated this guy 2a. So QH is 2 times a. A is root 5 over 3. So QH would be 2 root 5 over 3. Now we do the exact same story, but now on triangle ACH, using the angle bisector theorem. On that, we'll get the following: 9 over AP is the same as 6 over PH. And in a very similar way, let's isolate for the letters AP and PH. We go on this side. And we also know that AP plus PH is equal to AH, as before, which is 3 root 5. And this is what, in lowest terms, divide top and bottom by 3, get 3 over 2. So just like before, I can use some sort of lettering. I can use, say, 3b and 2b. And when I do, I get 5b is equal to 3 root 5, so therefore b is equal to 3 root 5 over 5. And I can now calculate one of the values. I'll calculate pH. pH is going to be helpful for me. pH is designated as 2b, and b is this, so 2b will be 6 root 5 over 5. And now we are in the final step. The final step is we have to calculate PQ. Well, PQ is pH minus QH. pH, I just figured out, was 6 root 5 over 5. QH, I figured out, was 2 root 5 over 3. And when you do that calculation, you get 8 root 5 over 15 for PQ. 8 root 5 over 15, and therefore number 17, the answer is D. What is the area of the region enclosed by the graph of the equation x squared plus y squared is equal to the absolute value of x plus the absolute value of y? Well, we have to first graph this, and then once we do, we will be able to figure out the area. So in order to graph this, I'm just going to concentrate on one quadrant. So if this graph is in all 4 quadrants, let's just concentrate on the first quadrant, and that is when x is greater than 0 and y is greater than 0. When that is the case, that equation becomes x squared plus y squared is equal to x plus y. And this is a little bit better to work with than this. So let's proceed. This, if you put it all on one side, becomes x squared minus x, y squared minus y is equal to 0. And at this point, I'll do something called completing the square. And completing the square will allow me to graph this equation. It'll be a little bit more helpful. So what you do is you take the coefficient before x, which in this case is -1, take half of that, which is negative a half, and then you square it. So when you square negative a half, it becomes a quarter, and then immediately you have to subtract that. Completing the square with the y is the exact same thing, plus a quarter minus a quarter, and that equals 0. And that allows you to factor this and this very nicely. X minus a half squared plus y minus a half squared. And then this and this we can put on the other side. It's basically 2 quarters, which is going to be positive a half. So this is a circle with radius square root of 1 over 2. So if I were to just draw the first quadrant, and we have to label the center of this circle, which is a half, and then we have to draw the circle in a way so that the radius is equal to the square root of 1 over 2. So r squared is a half, so r will be the square root of 1 over root 2. If you rationalize the denominator, it's root 2 over 2. So the graph looks something like that. But the key thing is that it's only got to be in the first quadrant, so I have to get rid of that portion of the graph because it cannot be in any other quadrant. So there we go. That is what it looks like just in the first quadrant. And if you use this equation, you can also get the x and y intercepts, and you get 1 being the x-intercept, which I have labeled here, and y being the 1 being the y-intercept. All right, well, when you do the exact same thing in all the other quadrants, you get the following shape. And as you can see, just as before, quadrant 1 is pretty much a part of a circle, but then all the other quadrants are also, in a very similar way, parts of circles. So now we have to calculate the area of this region. So to do that, there's a few ways, but I'll just do it in a simple way, which is connect these points, and when you do, you will get a square. And then, of course, on top of each side is a semicircle. So the area of that region will be the area of the square, which will be, of course, x squared, if that is the length of the side. And then we have 4 semicircles, so that's 2 circles. So 2 times pi r squared. So here we go. From here to here is 1, and so is that. So we can easily figure out x using Pythagoras. 1 squared plus 1 squared is x squared. So x squared is equal to 2, so x is the square root of 2. So a is equal to x squared, which is just 2. And then now we have 2 pi r squared. Well, r is the distance from there to there. X basically represents the diameter of those semicircles. So since x represents the diameter, the radius will be half of x, and that's root 2 over 2. So we have root 2 over 2 squared. So this is 2 plus 2 pi. Root 2 over 2 is 2 over 4, and therefore that becomes 4 over 4, which is just 1, so 2 plus pi. There we go. 2 plus pi is the area of the region that is enclosed by that graph, and therefore number 21, the answer is B. Tom, Dick, and Harry are playing a game starting at the same time. Each of them flips a fair coin repeatedly until he gets his first head, at which point he stops. What is the probability that all 3 flip their coins in the same number of times? So we have Tom, Dick, and Harry, and this is flip 1, flip 2, flip 3, and so on, right? So what I hope is I'll see some sort of a pattern. Okay, let's talk about this. If they all flip heads, there's only 2 outcomes, heads or tails. And if they all flip heads, if it's H, H, H like that, then that satisfies the criteria that they have all of them flip their coins the same number of times, and in this particular case, once. Well, what is the probability of that happening? Well, each of them has two outcomes, so the total number of outcomes, if I were to calculate probability, is 2 times 2 times 2. This outcome only happens once, so a probability of that happening is basically 1 over 8. So that takes care of flip number 1. Now let's say they all get heads on flip number 2. So H, 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 but this time on flip number 2. Well, the only way they could have ever gotten to flip number 2 is if they all had tails on the first one. Because if they got heads, if any of them got heads, the game stops. So they must have gotten tails, tails, tails on on flip number 1, on F1, and then heads, heads, heads on flip number 2. Okay, so getting tails, tails, tails on the first flip, well, in a very similar way, there's 1 out of 8 ways of the probability of that happening. This guy, 1 out of 8. And then we have to multiply the probability by the probability of getting 3 H's, which is also 1 over 8. So there you go, 1 over 64 is the probability of them getting all 3 flip their coins the same number of times, and in particular this time the number of coins is 2. Okay, I think we should be able to get a pattern by the next one, F2, F1, F2, F3. The only way it could ever get to flip number 3 is if they had tails, tails, tails on the first one, and again tails, tails, tails on the next one, and heads, heads, heads would have to happen on the third flip in order for the question to satisfy the question's criteria. Well, the probability of getting this one is 1 over 8. The probability of getting that is 1 over 8. The probability of getting this is again 1 over 8. So this is 1 over 512. Okay, I think that's enough. I think I've got an infinite geometric series. And the sum of an infinite geometric series is A over 1 minus R, where A is the first term, which in our case is 8, and the ratio is going to be you can just put the second one over the first one. So the second term is 1 over 64 over the first term, which is 1 over 8. And that's going to give you 1 over 8. Okay, so this is going to be 1 over 8 over 1 minus 1 over 8. And that's going to be 1 over 8 over 7 over 8. And when you invert and multiply, you get 1 over 7. And therefore, number 19, the answer is B. A set of teams held a round-robin tournament in which every team played every other team exactly once. Every team won 10 games and lost 10 games. There were no ties. How many sets of 3 teams, A, B, C, were there in which A beat B, B beat C, and C beat A? Well, there's 20 games, 10 games and that are won and 10 games that are lost. So the first thing I have to do is figure out how many teams there are. Well, there was 20 wins and losses combined. And let's just say the number of teams is n. Well, the number of games is n times n minus 1, right? Because each team plays every other team once. So this is the equation that allows us to figure out the number of teams. The n's cancel. So I have n minus 1 is equal to 20, therefore n is 21. So there's 21 teams. Okay, so the first thing I want to do is the total number of subsets. The total number of subsets where subsets are of the form A, B, and C, 3 teams. Well, since there's 21 teams, from 21, choose 3 teams. And that will give me the total number of subsets. And when you do that calculation, it's 1330. All right, so that's the total. But I'm not interested in the total. I want to know this specific situation where A beat B, B beat C, and C beat A. All right, well, the subsets that satisfy that condition, if you have a scenario where A beats B, B beats C, and C beats A. So basically, it's like a circle, right? A beats B, beats C, and C beats A. So this is the subset that would be what we're interested in. And the other subset is basically that doesn't not satisfy the condition, is any subset in which one team beats the other two teams. So for example, A beats B, but then A also beats C. So we have A goes to B and C. It beats both those teams. So what we have to do is figure out how many are in this category, subtract it from this, and that will give me this. And it's a little bit easier to figure out this, so that's what I'm going to figure out. So how do we figure out this calculation? Well, there's 21 teams in total, right? So for A, I have 21 choices for that first team. And then let's just say I choose a team, call it Team A. That team, which I have been called A, if you remember, each team wins 10 games. So it won 10 games. And of those 10, choose 2 to represent its win against C and its win against B. So that pretty much means from those 10, choose 2, and that, when you do the calculation, is 45. So to figure out the total number of subsets of this form, it would be this 21, the number of choices for that first team, times this 45. And that is 945. All right, so now we're down to the final step, as you take this 1330 and subtract from it 945, and that gives you how many subsets satisfy that condition. So 1330 minus 945, and that is 385. 385, therefore, for number 22, the answer is A.